Does it help? Okay, that's strange. Okay, so what did I do? I'm sorry. Okay, so well, I'll introduce the subject, then I'll describe the cohomology problem, which is important in constructing these democratic theories. Tell you something about the ingredients of the democratic theory and a few ideas about how can we construct some new theories of this sort. And many of you maybe heard already this part of the talk, which will be the major part, so I apologize for it, but well, not all of you. And this is a work in progress, so some stuff we understand, some stuff we don't understand, so okay. So what do I mean by democratic theory? I mean a theory in which all pictures can influence the result of the theory. And so there is this theory which was constructed 10 years ago, and the idea is of the theory is that it relies on an alternative but equivalent formulation of the cohomology problem, a formulation that Nathan introduced several years earlier. And the theory is cubic, it lives in the large space. It includes a single midpoint insertion that multiplies everything, and so this midpoint insertion does not enter into the equation of motion or the gauge transformation. And the theory also unifies in a very natural way the NS and Ramond sector, and at least formally the BV equation works fine. So it seems that all is nice, but why do we need all the newer theories? So there is a lot of criticism about the theory. And I mention here only 3 points. So one is a question related to the space of string fields. Because we have all possible picture numbers, the question is how and why should we restrict string fields as a function of a picture number in order to get something sensible. Another criticism is about the midpoint insertion. So it's only in the action, it does not enter the gauge symmetry and the equation of motion, but still if you want to get a propagator, if you want to gauge fix, all that can be a problem. And then also if you have everything, all the possible string fields, all possible components of the string fields at all Gauss numbers, then you also have to include negative conformal weight operators, and that could also lead to some problems. And there are other criticisms, plenty of criticisms about the theory, but these I think are the most, the strongest ones, and I'll say a few words about those. Okay, so the basic ingredient is this issue of the cohomology problem. So I want to say what is the cohomology, what is the formulation of the cohomology problem here, because this is the starting point. And okay, so what do we do when we formulate string field theory? So there's a series of steps which we usually follow. So the first one is to identify what the cohomology problem is. Then we extend vertex operators off shell and in a specific manner and say now we have string fields. We reinterpret the cohomology problem as defining equation of motion and gauge symmetry. Then we try to derive all that from an action, which would be a linearized action for an action that gives the linearized part. And to that we add interaction, so the equation of motion and gauge symmetry will now usually become nonlinear. And then we will verify that we really get something which is stringy. But really the first ingredient is this issue of the cohomology problem. So different formulation of cohomology problem would lead to different formulations, and we would be able to see maybe different aspects of the theory, maybe supersymmetry will be better viewed in one, or some other stuff will be better understood in one or the other formalism. And that's why I think that even if we have a new and really good theories, just seeing what we get from a different starting point is still important. Okay, so how can we formulate the cohomology problem? So there are several formulations of the cohomology problem, and the simplest, the most known one is that to work in the small Hilbert space, I mean, I'm talking about open string, so I have just one copy, and then you work in the small Hilbert space at a fixed picture number, and then you say, okay, this is what will be the equation of motion, the linearized equation of motion, this is what will be the gauge symmetry. The picture is fixed, the Gauss number must be 1, and this defines us what we want, and we can go from this theory and derive from it various formulation, Witten's formulation, modified formulation, etc. We can say that we want to lift all that to the large Hilbert space in a particular manner, and then we say that we want to replace the q psi equals to 0 by q eta psi equals to 0. So eta is the zero mode of eta. I just don't want to write the 0 all the time, but that's the only meaning that I have for it. And it means that I'm putting the physics at a copy of the small Hilbert space, which is in the large Hilbert space, that include the xi naught part. So the eta kills it, and then I just get the standard equation. But now, because I'm in the whole large Hilbert space, the other component of the small Hilbert space, I mean, the regular small Hilbert space, should all be interpreted just as a gauge degree of freedom, so the gauge symmetry is enlarged. And now I can again take whatever picture I want, but because of this, I have now a Gauss number 0. And this cohomology problem also helps us building a string field theory. So a Berkovitz formulation, for example, is constructed from this starting point. But you can have other formulations, as I mentioned. So one possibility is to work in the large Hilbert space at any fixed picture number and replace q by q minus eta psi equals to 0. And now delta psi would be q minus eta on some lambda. But in order to have psi at a given picture number, of course, you will have to limit lambda in some way, so it has one component at picture p, another component at picture p minus 1, etc. And the Gauss number of psi will still be 1. And you can show, maybe I'll show it, that you get just a formulation which is equivalent to these ones. And this, just like the other two, the previous two, is at a fixed picture number. The funny thing is that what happens when you allow for a range of picture numbers? So if you would take one of those and would just take a range of picture numbers, you will just have several copies of the cohomology problem. So it will be some sort of a doubling, etc. But if you are allowing a range in this formulation, then the cohomology problem does not change. And changing the picture is just a gauge transformation in this formalism. And in particular, you could try to say, okay, if I can take any range of pictures, why not take this lower bound to be minus infinity, the upper bound to be plus infinity, and just allow all possible picture numbers? So there is a subtlety with this idea, and I'll mention it. So how does it work? Maybe I'll say a few more words about it. So you have this equation, and it gives you a component at picture p and p minus 1, because it reduces the picture number by 1. And because, so if we are now currently still at a fixed picture, so these two must vanish independently, simply because they are supported at different pictures. And then you see that what you get from this single equation is the two equations that both q psi and eta psi, they both must vanish. So the result is that you have psi really in the small Hilbert space. So this time the xi naught component of the larger Hilbert space is the unphysical one, and the physical one is the standard small Hilbert space. And within the small Hilbert space now you have also the equation q psi equals to 0. So this is just the standard cohomology problem. So you see that it is equivalent. And now the gauge transformation. So again, lambda is composed of two terms, one at picture p, the other picture p plus 1. And if you want to get psi at picture p, then you see that they must be restricted in this way, as I said. And because both eta and q, they have trivial cohomology in the large Hilbert space, then it means that lambda 1 is eta of something, lambda 2 is q of something, and you can just combine these two components and say that delta psi is just q of eta of something, and that just tells you that you can just take eta lambda tilde is just an ingredient in the small Hilbert space, and then you get just the standard transformation also in the small Hilbert space, so it is completely equivalent, as I said. And as I said, if you allow now a range of pictures, then this equation will be just a gauge transformation, so let's see that. So suppose I have picture number P, and then this is the equation, and so it reduces to these two equations. And now I say, okay, let's define lambda to be just xi times this psi, and then delta psi will be just q minus eta acting on it. So when q acts on xi, it gives you x. X is the picture changing operator. And so the delta psi is just x times psi, so raising the picture by 1 minus the original psi, so you just remove the original vertex and you just have the equivalent vertex at some higher picture. And similarly, you can also lower the picture, so instead of working with this x, which is the raising picture operator, you can work with the other one, with the y, which is the lowering picture operator, and all is well. So you can just move using using your gauge symmetry, you can move from one picture number to any other picture number. Okay, now what is the problem if you have an unbounded picture? So if the picture is bounded, as I said, you can go to any value, but suppose now that you are unbounded. So I'm just introducing here as an example a string field which is unbounded. So I say, let's start with some vertex operator at a given picture number. Let's call it psi. And now let's add just all powers of x on it and all powers of y on it. So y is this inverse picture changing operator. And for now, ignore possible singularities from iterating picture changing operators. We can make it explicit by some explicit choice of the picture changing operator. So for example, by choosing the zero mode. But even if you just look at it formally, if you define this to be the picture changing operator and just act on it with x, you just get this psi tilde back. So you see that you can define something that will be an eigenmode of the picture changing operator, and of course you cannot change a picture for such a state. So there are states whose picture cannot be changed, and this can only happen because I'm taking something which is unbounded. So the result is that you must somehow restrict the space of string fields, and the issue here is that you are putting a copy of the same size in some sense in all possible picture numbers. So of course, I mean, if you try to imagine having some sort of a norm or something like that, then this would be just a state with an infinite norm. So we don't have a norm, but suppose we had, then that would be the problem. Okay? Okay. So, okay, that should have been psi. So, okay, so in principle, this by itself is not a problem, but if I'm saying that I want to be able to move the picture from one component to other component, and then I have something that is invariant under picture changing, then of course I cannot move its picture. So this state... No, it does not have a definite picture, but the point is that if you just had a vertex which is supported on some range, finite range of pictures, you could have introduced gauge transformations that move the whole range to any particular picture number. But if I'm giving you this state, you cannot move it to any picture number because just act on it with x, act on it with y, nothing happens, it is invariant. So this is like the most extreme example of something of this sort. But you do not have to insist that you will have an eigenmode in order to claim that you will get something that you cannot really move to any particular picture. So we have to restrict the space of string fields, and some sort of a natural restriction would be just really to say we want to consider only a space of string fields that we can, in principle at least, move to a given unique picture number. Okay, so that's supposed to be psi, and suppose that this psi has some unbounded picture. We can try to move the picture, different components, different picture numbers one by one. So let's suppose we have this psi, and we act on it first with something like that, q minus eta on xi on the component and p naught minus 1. So the idea is that I want to remove all components and to be left only with picture which is p naught. So in this way, I just kill the component that I had at psi p naught minus 1, and I replace it by something which is supported at picture p naught. And now let's take the second gauge transformation, which will do something similar, but to the component at p naught minus 2, and go all the way to minus infinity in this way. And now if there is no really problem with this particular string field, then you can end up having something whose components which are smaller than p naught all vanish. And similarly, you can do also a similar thing with all the higher components, just working with y and replacing this xi by p, which is the contracting homotopy operator for q. And then all will be well. But now if you want to see what you get at the end of the day, you see that what you get is just the original component that you had at p naught, plus the picture changed and the picture changed at all other values. And then the question is simply whether this series is absolutely convergent, because if it is not an absolutely convergent, again you say, if I'm starting with some string field, and when I try to implement that, I'm getting here a series which is not absolutely convergent, then this state is outside my space of kosher string fields. So if you would take just the psi that I had before, this eigenmode, and you will try to do this trick, then you will end up with just infinity times the original thing which you started with, because all this will be just exactly the same. Okay, so then you will see explicitly that, yes, this state should not be taken as part of the definition of my space of string fields. And similarly, you will also get at p naught minus 1 a non-absolutely convergent series. You would like to get a series which converges to 0, but you will just get a divergent series, or at least a series which is not absolutely convergent. So you will say, okay, something here goes wrong. I should not consider this these states. Okay, so this is about the cohomology problem. So we understand the cohomology, we understand the problem with taking it to infinity. We sort of understand an idea about how to resolve this problem. And again, people can claim that, okay, you do not give really a completely explicit mathematical definition of how to define the space of string fields, but then we never have it even for the bosonic theory, a really well-defined, concrete definition of the space of string fields. We always have some problems there, so we understand, at least in this case, in this context, what is the problem and what in principle should be the resolution. Okay, so now I want to describe what else goes into a construction of the democratic theory. So again, I apologize for the people that already heard it a couple of times, but okay. So one thing that we use is these multi-picture changing operators and their potential. So I want to introduce those. So as I already said, as as you all know, in the large Hilbert space, Q and eta have trivial cohomologies, and we can see it by the fact that they have these contracting homotopy operators. So I just define this Xi to be O1, and this minus 6 C dic C e to the minus 2 phi to be O0, and they're contracting homotopy operators because Q on O0 and eta on O1 both gives me 1, and this is a proof that the cohomology in the large Hilbert space of both operators is trivial. And then I can also ask what happens if I'm acting with Q on this O1 and with eta on O0. So again, as you know, in this way I'm getting the picture changing operators. But we can extend this structure to other picture numbers. So I say, okay, if I have X, then I can get X from Q acting on an operator. And in this way, I get this O1. So now if just imagine that P equals to 1. And when I'm acting with on this O with eta, I'm getting 1. And 1 is a picture changing operator of picture 0, so it does not change the picture, and that's why it is really 1. But I can also do the other. I can also go the other way around, and if I have this y I get from eta on O0 because O0 is the one. So if I'm starting with the 1 and say, okay, I get to the 1 from O, then now when I act on it with eta, I'm getting a lowering picture changing operator, and I can in principle continue in this way ad infinitum in both directions. I can define these operators OP and these operators XP, which will be multi-picture changing operators, and the potentials, let's call for multi-picture changing operators, and all this diagram will work fine. And all these operators, the O's and the X's, can be defined to be weight 0 primaries, and if I also want them to be completely universal, then their definition is even unique. If I don't want to have complete universality, then there's the freedom of adding to these terms some exact terms. Okay, so what question? Okay, so what was the linearized theory that this democratic linearized theory? We say that okay, we want to have the equation of motion to be q minus eta on psi equals to 0. And in principle, we could have said at this stage that this psi has any particular unique picture number or any particular range of picture numbers, but we will see that in fact the range must be infinite. So in order to get it, so the most natural guess would be to say, okay, let's have an integral of psi times q minus eta psi. But then when you check what is the ghost number and what is the parity of this expression, and you remember that this integral is an integral of the large Hilbert space, you see that you must insert some operator there. And then you say, okay, if this psi has some given picture number, this O must include xi, because I know that the physics lives in the small Hilbert space in this psi. So I must have some xi in order to saturate the xi0 mode in the large Hilbert space, because the integral is in the large Hilbert space, because psi lives there. And now, if I'm saying that this operator commutes with q minus eta in order to get something which is really symmetric with respect to these psis, that this fixes this initial condition of xi, fixes this O to be just the doubly infinite sum of this OP, these potentials which I introduced before. Okay. And now what was the democratic theory? So the proposal was to say that, okay, this was the kinetic term, and now you can just add here a cubic interaction, and this O will be just a midpoint insertion, because if it is a midpoint insertion, then it commutes not only with q minus eta, but also the star product that I have here in the definition of the psi cube also is fine. And then when I'm deriving equation of motion and gauge symmetry, this will be the equation of motion and the gauge symmetry. So, so for the gauge symmetry, this is sort of obvious. For the equation of motion, you would have said that, okay, you should also have the O multiplying all this story. But then my understanding is that string fields could never have supported the string midpoint, and people may argue about that as well. But That's my understanding. And then if you have something which is supported at the midpoint, times something which cannot have supported the midpoint, then the only way in which it can hold is if this other component equals 0 by itself, at least as long as the thing which is at the midpoint is not by itself 0, and it is not 0 by itself, this O. We know that the criticism of some old string field theories included criticism of all sorts, and one was that the gauge symmetry does not work fine. So for Witten's theory, for the modified theory, we know that the gauge symmetry does not close and it leads to singularities because of midpoint insertions. But here, because there is no midpoint insertion in the gauge symmetry, there is no such problem. But still, if you want to define a propagator, and so you first fix the gauge partially to get some given picture number, and then you can get something like Witten's theory and what is the propagator and so on. So this is the problem, and the question is how can we hope to resolve a problem of this sort. So that's why we want to construct new theories. We believe that starting with this starting point of a different formulation of a cohomology problem can lead to some insights. So despite the fact that we have really nice formulations now, we want to see what can we get from this starting point. But we have to modify these theories a little. Also, so this is very simple. You just say that Psi is the sum of Neve-Schwarz plus Ramond. And all works fine. You don't have to change anything. So it's not only that you get it with the correct equations of motion, at the linearized level and the interactions. It is very natural, the unification. You just say Psi is Neve-Schwarz plus Ramond, expand, and that's it. And you will not get in the gauge symmetry. You will still have this thing without any midpoint insertion. So, for example, the modified theory, you remember, so they said, okay, now we have the gauge symmetry, which does not lead to singularities. But then when you reiterate it to the third order, you see that you have singularities there because you put midpoint insertions on string fields, which you should never do. But here you cannot get any problems of this sort. Yeah, of course. You get the standard kinetic term. You will get just Q minus eta on the Neve-Schwarz and Q minus eta on the Ramond. That would be the equation of motion. And then you will say, okay, it means that because if you consider now different components at a given picture, then it will tell you again that, okay, you are in the small Hilbert space and Q on the string field vanishes. So this is just the standard equations that you would expect to get. And the interaction is also a sensible one because what you will get here is just a Neve-Schwarz times Ramond squared. That would be the interaction. Okay, so what do we need to construct new theories? So as I said, the problem is that, one of the problems is that we have the insertion at the midpoint. So we want to replace O by some other operator which is not supported at the midpoint. So for example, just to be concrete, you can decide that you take the zero mode, but you don't have really to insist on it at this stage, just to take something else. But if you take this, then you see that this is a BPZ even operator. So at least at this linearized level, it looks fine. And now, but now the free equation of motion includes this O. And now I cannot claim, as I claimed before, that I have something at the midpoint and something, a component with the string field which is not at the midpoint, and then the result is that I can just ignore this operator. Now I really have an equation which looks not quite the way that the equation of motion should have looked. So the question is whether I can take care of it, or so whether I can somehow cancel this O tilde. Now, schematically, again, forget about singularities. This O tilde is something like C times an infinite powers of x to the n, and when I understand the negative powers as positive powers of y. But, okay, so you could say, okay, forget about Xi, this is part of the measure. I'm not sure if it's really a good argument, but even the sum with the x's you cannot invert. You cannot cancel it out. And this is a problem. So what can we do to solve this problem? So one idea that we're thinking about is to take just half-infinite picture. So you define instead this O tilde to be a sum that goes from 0 to infinity. Okay, not from minus infinity to infinity, but from 0 to infinity. Now, of course, now you have the problem that the commutator of this q minus eta and this operator is not 0. And that was a problem. That's why we took in the old formulation the range to be doubly infinite, from minus infinity to infinity to begin with. But the thing is that a value of an operator depends on the space on which it acts. So if I'm saying, let's take now psi, the string field itself, also to be just one directional infinite, so go from -1 to minus infinity without the positive numbers. And I mean, just to be concrete, you could have taken different ranges both here and here as long as they touch each other in a proper way. Then if you are doing that, then this -1 will just lead to something with a picture number that drops out under the integral, so it's not important. And then you can say that, okay, this is the action. You get an equation of motion which look just like before, only with some term, some initial condition from this top component, and we should still understand what to do with it. But if we just forget about this term for now just act on this equation with eta minus q, and this will remove this O tilde, and then you will remain just with what you would like the equation of motion to be. Again, modulo the last term, which I don't want to talk about. Also, because now this operator includes just this sort of a sum, which you can at least formally write in this way, you can just act on it with 1 minus x. And again, if the string field is decays fast enough as a function of the picture, this formal algebraic manipulation will just give you cancellations between components at nearby picture numbers, and you would be able to cancel this factor just by operating on this equation with 1 minus x. Okay, so now you could hope at least to have an equation of motion, which is really the equation of motion that you need. Okay. What about gauge transformations in this case? So one of the reasons for using all pictures, other than the fact that then you get this midpoint insertion properly, is that if you look at the nonlinear, at the linear gauge transformation for the interacting theory, then you will have something which looks like psi lambda commutator, and for simplicity now consider just what we had in the old democratic theory, which is just the standard cubic vertex. And then you know that if psi has picture number and lambda has some other picture number, then this component will have picture number which is a sum of those. But then because this is just the linearized part of the gauge symmetry, and you know that you will need to iterate it ad infinitum, then you will see that in the next iteration you will have picture psi plus 2 picture lambda plus 3 picture lambda and so on. So if lambda has a non-zero picture, you see that you must include all the pictures that goes all the way to infinity or to minus infinity. But the thing is that we do not have to insist on having both. We can decide that we can have only one of those, just as what I suggested here. And then we will say that we allow the picture number of lambda to be a non-positive, and we also must restrict the zero component to obey this equation. Otherwise we will have also contributions to psi at picture number 0, which we do not allow. And now there is no problem, because the gauge transformation just gives you what we had already here. All negative picture numbers, but no positive picture numbers whatsoever. So there is no problem with closing the gauge transformation, at least not in this simple formulation of it. Okay, so the next thing would be to add interactions, and we are not sure yet how exactly this should be done, but one observation is that since the insertion now is not a midpoint insertion, then we cannot just say that, okay, we take the same insertion on a cubic vertex, and that's the end of the story, because this will not be symmetric this time. And presumably this will just lead to, as in other cases, to an A infinity structure, and we will need to define really higher order vertex operators. And then these higher order vertex operators would somehow be achieved by gluing the insertions that you have on the first vertex. So in principle, you would expect to get something which will look like this C times powers of the insertion that you had other than that. And now you can make sense out of it, because if the sum would have been doubly infinite, like what we had in the previous formulation, then this would make no sense, because it would just lead, when you would just take a square of this double infinite sum, you will just get infinity times the sum, because you have just all possible pairs from both directions to contribute at any given picture number. Also, this two-directional series, even in the most naive interpretation, has a zero radius of convergence. So that's also a problem. But now this is not a problem, because you can say that, okay, I'm just opening it, and then I have 1 plus 2x plus 3x squared, etc., and all is convergent, because at any given picture number, you just have a finite number of terms that contribute there. And then it suggests that hopefully we will be able to define such a structure. So this is something we're still working on. And, okay. So it also seems that we will have to further restrict the space of string fields. For consistency, we will have to impose some sort of a restriction, which will be like x, y on psi equals to psi. And, well, this xy by itself is not a projector, but this is a projection equation. And this projection equation is well defined. I mean, this will commute with the Gauss number, picture number, and conformal weight. So this is an equation which is defined separately on finite dimensional blocks. So you can just interpret it independently on each such block, find the complete solution, in principle, at least in each such block. And this is a linear constraint, so there is no issue of how to implement it. So there should be no problem with this. On top of it, it seems also that if you apply it, it will automatically remove the negative weight states, so you will not face problems related to these states as well. Okay, so what do we want to do now? Sorry. So if we manage to do all that, then the inclusion of the Ramond sector would remain straightforward, because just like previously what I said, we just have to take the Neve-Schwarz and just add to it the Ramond and expand and see what's for the Ramond, what's for the Neve-Schwarz. The same would remain true. So it not only be simple, it will also be natural in a way. They will naturally be unified. Then the BV master equation, because it would have to automatically hold, of course, assuming that we will be able to construct all these higher order vertices. And presumably such a theory would give a framework from which other known theories could be derived. So like the old democratic theory, from it you could with some playing with it, with some assumptions and some partial gauge fixing derive from it the Witten's theory, the modified theory, the non-polynomial theory of Berkovitz. So presumably, if we will have some formulation of this sort, we'll be able to derive from it other A infinity theories, and it could be useful for other stuff. Of course, the theory now is not really democratic. It's more of the democracy that we practice in my country. So only half of the population contributes. But the important point here for me is not really the full democracy, but the starting point, which is a given cohomology problem, which gives us like a different perspective on what string field theory is and maybe what string theory is. So just some more thoughts, and I'll finish with that. So we have to examine whether it is possible to obtain such a democratic theory. And then the next thing would be to see if we can, with gauge fixing, to obtain some new formulations which we did not had before. And maybe we can get some new expression for scattering amplitudes. And then if all that works fine, then at a very later stage, extend all this story also to closed and heterotic theories. And that's it. So thank you.